I think there's a couple more minutes. So
Okay, that's it.
let's give it a few other minutes.
like a cinema, right?
Trying to be too comfortable, but
Yeah.
It's like this movie theater.
like at the movie theater. Right?
Need some popcorn.
We went out.
Okay. Let's start. So good morning, everyone. So now we present to you the off-heap FST construction in Lucene, inspired by Tantivy. Right? Yes. So go ahead.
Thank you. So hi everyone. So nice to meet you today. So this is my first Apache conference. So it's nice to meet and discuss with Apache developer from all over the world.
Door.
So
can we hear him? Close the door because it's kind of noisy coming from
today is yeah. So today I've been so my name is Dzung and you can call me An, and I'm a software engineer in Amazon Production. So today I've been be sharing about one of the features that we implemented for Lucene, which is Off-heap FST constructions. But first, may I ask how many of you are using Lucene or aware of the Apache Lucene? Oh, so yeah, so that's a lot. So yeah, so for someone who doesn't know what Lucene is, so it is a Java search engine library that can help you index document and search from those documents using the inverted index algorithm. And for the work I'm presenting today, it is inspired by Tantivy, which is a Raspberry search engine library, and itself, so Tantivy itself is also inspired by Lucene. So along the talks, I will explain what FST is and why it matters, and some of the challenges in the Lucene designs and how we improve it. Okay, so but first let me tell you how lexical matching is done in Amazon Product Search. So I think it is not maybe not too specific to Amazon, but all of the e-commerce search system with using Lucene might also do something similar. So basically, for searching in the e-commerce, we have the customer queries and the async products. So in Amazon, we call it asyncs. So we need to match the queries and async products. And what we are doing is that we both the queries and the async product will go through a Lucene analyzer. So the analyzer is just compositions of different text normalizations. So the normalization usually requires some form of data from, for example, synonyms or stemming or compound dictionary. For example, someone can add a synonym between PS and PlayStation. So to allow the customer to search for the PlayStation products with the PS as a keyword. Or if we enable the stemming, then the customer can search using both the plural form and the singular form. And so in Lucene, Lucene has many data structure to process the normalization efficiently. And amongst those data structures, so FST is a very important data structure. So it powers many critical components in the Lucene index, from the term index to the synonyms, stemmings, autocomplete, and many more. So what exactly is FST? So it stands for the finite state transducer, and basically it's the finite state machine that has the input depth and output depth. So because we have both input depth and output depth, so in Lucene we use this as the type of complex and memory efficient math. And you may be asking, so why Lucene need to reinvent the wheel? So can we just use a very simple Java hash map? So here is a quick comparison. So with 2 million English token, so about 5 characters each, with the integer output. So if we're using a FST, it only have 12 megabyte in the final size. But if you use a nice Java hash map, then it is about like 200 megabyte. So that is almost 20 times larger than FST. And it gets even more interesting. So out of the 200 megabytes, so only 30 megabytes for actual data. But the rest of the memories are just for the Java object structure, like class pointers or backward or object attribute and so on. So using the Java hash map, we are paying like 5 to 6 times memory overheads. But why doesn't even matter? So if you are working with Lucene, then you may already know that Lucene application usually have a very small heap, maybe just over a few gigabytes, and the rest of the memories are the off-heap memory, which the Lucene used to like catching and speeding up the Lucene index. So the less heap memory you need to use, the more off-heap memory you can allocate to speed up the overall system. So that's why it's like having a heap efficient data structure is very important for the Lucene applications. So how exactly the FST achieve that? I can show like a simple example on the next slide, but you can think of FST as just a compressed prefix tree, which also has the suffix sharings and also has output. So in this way, FST can share the prefix and suffix across millions of strings, so making it very memory efficient. And not only that, so instead of instead of storing millions of nodes as millions of Java objects, so the FST store everything as a compacted and block by array data structure. So that making we will avoid like the memory overhead due to the object structure that we mentioned earlier. So here is one example of the very simple FST. So it represents as the directed acyclic graph, and to traverse from it, you can start from the starting node on the left and just follow the arrows and go all the way to the end node. And along the way, you build up the input and the output. For example, like if you go on follow the top part here, M, O, and P, then you will get the good morph, and because there is no output, so the output will be 0. And or you can also follow the part of S and T, O and P to get the word stop. And because we encounter 3 and 1 as the output, so the final output will be 4. So as you can see, like not only we can share the prefix like the M and O here, but we can also share the suffix like the node P here for the word stop and stop. So the below table is just a simple representation of the same FST. So as you can see, it's just like a normal map from string to integer, but it's just like that it's more memory efficient. And similar to a map, so FST also have many useful operations. So at the view time, you can add an input and associate with an output. So it is similar to adding an entry to a map. And at the query time, not only that you can get exact lookup similar to the map would get, but you can also have a prefix because it's a prefix tree. So you can get have a prefix traverser. So to get all of the entry with the same prefix. So it not only like support exact matching, but also like prefix matching. And now, so let's talk about the motivation. Why do we like need to improve this data structure? So to give a bit of background context, so when Tantivy, so again, Tantivy is the Raspberry search engine framework, which is inspired by Lucene. So when Tantivy was first released, it was benchmarked against Lucene, and so surprisingly, so Tantivy outperformed Lucene in many types of ways. So we did a direct comparison between Lucene and Tantivy to see how they are different and whether there any optimization in the Tantivy that we can borrow to speed up Lucene. So my colleague Tony here will talk more about this on Sunday. But one of the key difference is how the term index are organized between the Lucene and the Tantivy. So here's the quick illustrations of the term index in Lucene and Tantivy. So as you can see, so both Lucene and Tantivy are using FST to store the terms. But the difference is that the Lucene FST can only be constructed on heap, and due to the memory constraint, we can only store the most common prefix in size term index. And in each entry, it will point to this block where it contains all of the data for the actual terms. So in order to do like a term lookup, we first need to traverse from the FST, and then we do another scanning to get to the actual term. But for the Tantivy term index, so it also using FST, but the Tantivy FST can be constructed off-heap, and they can build a very large FST with a small memory footprint. So that allow it to create a single FST for all of the terms inside the index. So in order to do a term lookup, it only requires a single FST traverser. So that makes it more efficient than Lucene. So another motivation for this work is the real story from Amazon. So during one of our migrations, so we saw a 10% increase in our Lucene code, and we, after doing some profilings with the Visual VM, so we chased down it to a single method, the read by method inside the FST. And so here's what happened. So before the migration, so after we build the FST, we will save it to a file to a data output, and then we read it again later. But after the migration, so after we build FST, we use that directly. So the read by method to read from the FST to traverse from the FST is different between the two cases. And so so here the implementation of the two read by method. So why time complexity wise, so they are both O1, so truly like random access, so they should be like having the same performance. But due to the zip method inlining that we found out, so the method on the left is simple and they will be inlined by the JVM, but the method on the right is too complex to be inlined. So that zip discrepancy alone causes about 40 to 50% latency regressions in the FST traversal code. So yeah, so Lucene FST has a few problems. So not only that it does not allow the off-heap constructions and preventing the larger FST, but in on-heap implementation we also not very efficient. So this gives us a clear opportunities to improve this Lucene core data structure. And the solution to this problem is again inspired by Tantivy. So they have a very easy to understand blog post on the solutions that you can read later. But the key observation is that the FST is by nature streamable. So the input of the FST need to be sorted, and because they are sorted, after we adding an input, we can be certain that there will be no other input with a smaller prefix can be added to the FST. So that means like you can stream the previous node to the list and forget about them. So only the frontier node, which is the node that you are adding, need to be stay on heap. So here's the quick illustrations. So suppose we already have an FST that had the node M, O, N here, the node 1, 2, 3. So and now we're adding a new input, T, X, U, R, S here, the 4, 5, 6, 7, 8 node. So if you look at the node 0 on the left, so because we are adding a new X, T to the node, it means that there will be no input, no other node can start with M. So it means we can just free the node 1, 2, and 3 here. So just stream them to a data output and just forget about them. And similarly, when we add the input PUES here, so we can be certain that now the node can start with TH. So it means that we can also trim the node 5, 6, 7 here to the disk and forget about them. So all in all, that means we can build a growing FST with just more or less constant memory. So only the node, the frontier node here, so 0, 4, 8, 9, and 10 need to be stay on heap. So yeah, so the solution is simple as such. But what about?
Can I just ask a question? Because
Yeah.
if you do that, then the nodes are not being streamed in the node ID order. Is that a problem? Like you skip 4, you know what I mean? Like if you stream them out, it goes 1, 2, 3, 5, 6, 7.
Yeah, I think so. In terms of implementation, I think the node can have a link to another node, so it you don't need to have exactly like
In order,
continuously.
yeah.
But I think like most of the nodes here will be written continuously when you are adding them. So I think that will make the caching a bit more caching friendly.
Yeah.
And so I think there are also some other issue like whether because the FST is not being written in backwards, and we also having some discussion about like whether we need to make it forward so that it's more caching friendly. But,
Sorry, I didn't want to derail you too far.
Yeah.
Thank you.
Okay, so what about the suffix series? Because after all, that is one of the main benefits of the FST. So back to this example. So here, after we stream the node 3 here to this and we forget about it, then after if we want to add the node 5, 6, 7 here, we need to point the node 7 to the node 3 instead of creating a new another node. So that means that we need to have a way to read from the same files that we stream to identify a possible suffix while we are still writing to the file. So in this list, we propose to use the file channel for concurrent read write. So that means like we can like read from the same file while we are still writing. But this proposal has like one big problem. So we need to open the index input while the index output is not closed. So this is forbidden by Lucene for good reasons. So the Lucene I/O model is following the write once with many model. So that means the data is visible for reading, so it needs to be immutable. You cannot like modify the data. So that makes like sharing and caching to be more efficient. So obviously, so having a concurrent read write will break that model. So eventually, we follow the same approach as Tantivy. So we're using a caching. Basically, like we can have a read reason use cache for the most common suffix. And here is an example of the suffix of the So before, because the FST is fully on heap, so everything is inside the memory, and we can have basically a simple node hash. So the node hash is just a way to identify a similar suffix, and the node hash can point directly to the FST in the memory. But now because the FST, most of the FST will be inside this, and only the frontier node is inside the memory. So we need to have a separate caching here. So it is like just the replicas of the FST. So in order to make the FST, so one of the downside of this approach is that to have a fully truly minimal FST, so we need to have like every node inside the cache. So in order to find all of the possible suffix, we need to have all of the possible nodes. So it means like we need to have a double heap memories for to make it truly minimal FST. So with that kind of defeats the purpose of what we are trying to do here. So, but luckily, so in practice, you like almost never need to have the double memories. And so here is one graph about the relationship between the size of the FST and the size of the subcache. So this FST is built from 20 million crystals, and the original size is about 1.2 gigabyte. And as you can see, the more sophisticated we have, the smaller FST will become. So that makes sense because like if you can like reuse if you can reuse more suffix, then the size of the overall size of FST will become smaller. But increasing the suffix size beyond certain point doesn't have that much, and that keep diminishing return. For example, like in this case, like if we have the suffix to 192 megabyte, so that already makes the FST to be more or less minimal. So there's no reason to increase the card size beyond that. But in practice, you don't even need to have that, and a smaller memory also works. So of course, like you can use the Lucene benchmark tool, which is a very powerful tool to benchmark the Lucene applications. So you can run the benchmark with your actual data and to find a possible suitable value for your use case. But key point is that like we don't need to have a very large memory just for this socket cards. And so the result is that so building the FST now we can stream it to any data output. So not only that it support to be with off-heap, but the on-heap, building it on-heap also more efficient. So for the on-heap use case, if we use the bi-array output stream, so you can get back the 50% FST performance from the zip inlining problem that we saw earlier. And for the off-heap use case, if you use the file output stream, you can like build a very large FST with small memory footprint. And here an example, so the FST monitor test. So we try to build 2 billion nodes of in the FST. So now we only need 30 megabytes. But if we use on-heap, it will require about like 35 gigabytes, which is the huge memory usage.
1,000 times smaller. Factor of 1,000.
Yeah, that's true. More than 1,000 times.
More than 1,000.
Yeah. So to give a bit of reflection, so there are 2 important lessons we learn along the way of this works. So first, this is a healthy inspiration within open source community. So the Tantivy is inspired by the Lucene architecture, and Lucene is also inspired by many improvements in Tantivy, so making both of the applications better. So this is open source at its best, like everyone wins. And the second important lesson is that the early discussion with the communities is very valuable. So our initial proposal using concurrent read-write wasn't a fit for the Lucene core philosophy model. And by discussing with the communities early, we avoid wasting time and make sure that like, the development is on the right track, so we are doing the right thing. So
And there's another talk about the Tantivy Lucene collaboration, right? Tony, when's your talk?
That's Sunday.
Sunday.
Around 5.
Okay.
Hope people are still there.
Yeah.
So for the follow-up of this work, so we want to explore the option of building off-heap FST in many Lucene components. So one of the ongoing efforts, not by us but by communities, is having off-heap listener builder. And another question that I want to ask the communities is like whether we should also do this for the Lucene term index. So by the time of this talk, so I think Lucene has switched to like simpler implementations that only have the prefix using the simple child. But I think like having it to be off-heap and like to make we can build a very large child with a small heap memory is still valuable. So so to closing out, I also include several links to the important discussion and code here that for someone who want to dive deeper later. Thank you. Please.
Question? Great. So one of the comparisons you made with Tantivy is you're saying Tantivy, I don't know if I'm saying that right, but the complete term dictionary is in the FST with Tantivy. Lucene is awesome. Lucene, we have abstractions, we have postings formats, we have a number of postings formats. One of them puts the entire thing in there as well. Did you use that one and compare it?
So that one is I think
The FST postings format.
yeah, that FST posting format. I think it's the experimental format. So I think like we would only also have run comparison between them, and
I can help on this. So, I don't think it's first of all. I don't think it's experimental. I think Lucene users can feel free to use it. It is supported and it works. And even that, we compare with it, it's still not as fast as Tantivy. But there's still minor differences in how things are organized. Because Lucene's FST, I mean, it sort of extends to my talk, but it's more or less a Java problem. Like, in order to use this FST, if you look at the code, FST is generic over a type of an output. So you can use FST to address many different kind of outputs.
Yep.
And it does have an object overhead. So actually the less data you want to use for your output, the more you're paying with that boxing. In one of my experiments, I simply want to output on long.
Yeah.
And then it got boxed into a Java long. Huge amount of allocations and slowdowns occurred because of that. So to our original question, yes, we tried, and even with that, we're still slower. I mean, Lucene. We're biased on Lucene.
But that could have been a useful intermediate benchmark. Like at first we saw this difference, and then by making it similar to Tantivy, then how much better do you get? I have used that one. And I also found that the FST postings format, I think it put way too much data in the value side. Right, I just wanted a long. I wanted a pointer actually to the postings data. I didn't want to actually put the postings in. But I think the FST postings format puts everything, which I'm not sure if there's an option.
Yeah, we can connect offline. I have one of the PRs on Lucene that actually tried to implement a FST to just the postings offsite on disk. So FST to long.
Nice.
That didn't go very far because this is great for primary key lookup use cases. So if that meets your need, awesome, take it. But the overall is not a well-rounder because the lot of prefix-based queries like fuzzy queries or intersections, especially FST, unfortunately, that's still slower. It cannot even beat the current prefix-based implementation because the way the FSTs are organized, especially when accessed off-heap, they're not very random access friendly. So we're paying a lot of I/O performance degradation there. So actually for prefix or wildcard, any sort of that kind of operation, the prefix format on the left is actually more computer friendly to run fast. So that's our learnings. I can share the link to the PR later.
We can go with you as well. I was also toying with using the FST postings format, anticipating some major wins, provided I had memory or whatever, and I didn't quite see it.
Yeah. If you don't need any sort of a wildcard prefix query, then you generally will get a win.
Yeah.
And with the community continuing improving FST, I think you can get even more.
Okay, please.
Just curious, since you mentioned that one difference is that the terms need to be sorted first before you use this new approach. So do you not count the resources for sorting in the benchmark? Or is it a negligible amount of resources like RAM or this?
I thought Tantivy also requires pre-sorting before building its FST.
Yeah, so in the terminal, so we need to the term is already sorted. So
But
when it comes to the FST.
Tantivy's FST construction is also pre-sorted, right?
Yeah.
All of these FST construction algorithms need the pre-sorting.
Correct, but when does it get sorted?
Yeah, it's outside of the FST.
Before this talk.
Yeah.
Before.
I guess it's up to the client using FST to sort it first.
Right. So usually these search engines, they buffer before they write things to disk. They just sort of buffer every incoming index activity, and at some point when you decide to write, some preparation work, including sorting, happens.
But also, it'll happen during merging, and that's when you'll get even larger and larger runs of these, and then they will be merging two pre-sorted lists, so you won't have the same overhead.
Yeah.
But yeah, because I had the same question. So did you see an overhead because you had to include pre-sorting in this approach, like when you look at it end to end, or was that not?
Can you ask the question again?
My question was similar, and I mean, maybe I picked some concepts wrong. So first of all, thanks for unpacking a very technical topic, and I really need to go through all the links, but you know, it's really informed me about some FST stuff which I wasn't aware of. One of the takeaways, and I think he had the same question, is that we did not require pre-sorting earlier, but you need it now.
We've always required pre-sorting.
So pre-sorting is required for.
It was always required?
Yes.
Yeah.
Okay.
Nothing new.
In order to make so before, in order to view minimal FST, the input need to be sorted. And I think there also a link to a paper so that
So the input that was passed to FST was always sorted. We were just not making use of it to freeze the nodes while constructing it.
Yes.
Okay. I see. So that's why you don't see the additional overhead now. Okay, that explains it.
okay, please.
So the 35 gigs of on-heap memory just ended up moving off heap. It doesn't save any memory in the grand scheme of things, correct?
Yeah. So
No. It's like temporary memory that's used during construction. That's not persistent. The size of it has nothing to do with the size of it. Well, something to do with it.
So
It moved off disk. The size of the FST that's being built is 35 gigs. It just writes it directly to disk, spools it to disk instead.
I really okay. Maybe I missed it, but I thought there was all this object overhead that we were saving
So
during
I think there's a
construction.
bit of overhead, but because the FST data structure is already like efficient to like avoid like minimal overhead. Maybe like you have some few maybe kilobytes of data from arrays and all of those. But yeah, I think so. Usually like the memory is it will be similar to the size of the final FST when we build it. So, but it's just before that, like we need to build everything on heap, and we dump everything after that to the disk. But now we can like stream it to the disk while we are building.
So instead of being off heap going to memory, it's off heap going straight to disk.
Yeah. So, but also like you can use any type of data output. So like we don't like assume that is the disk or RAM, but as long as you can provide data outputs, then
Append only.
yeah.
Just write the bytes out.
So that was one of the benefits of data outputs. So we can just like put everything there and it abstract IO. So we can change it from. So we also support the on-heap and off-heap use case. Even if you want to do on-heap, it's still possible now.
So I think you addressed this at the end, but I didn't quite understand. Have we tried using this to create determ index, like as Tantivy did, like the whole like avoid having that block, the separation between the FSTs and the blocks? Maybe that's what you guys were all doing.
Yeah, that was the FST postings
That's
for
what was
it.
mine was
sorry.
bringing this up. It
Yeah.
already exists. It's already in Lucene. It's been there for many years.
Got it. Okay.
I've even used it as a default for certain use cases.
One thing you didn't point out that's a cool history here is that awesome blog post about Tantivy's FST, right? I highly recommend reading that blog post. It really gives you a good introduction and the scale of the problem. He quotes Lucene's FST implementation as inspiration. So Lucene built this one first, then the Rust authors created this amazing implementation being inspired by Lucene's, but it's better because it's spooling things to disk, it has other improvements. We see that and we fold it back into Lucene. It's just a great example of how open source works.
Yeah, that was on your slide. That's yeah.
Oh, I missed it.
Great. Yeah. Can I?
Okay.
One other question I have. There was a limitation of Lucene, the WORM, write once, read many. Maybe someone in the room could correct me if I'm wrong, but I thought that if I wanted to rate a custom postings format, let's just say, that as long as, I mean, if I need to read a file, write a file, I thought I could do whatever I want as long as the output is finally this read-only finished thing. And am I incorrect in this belief? Or maybe I can do that. I can get away with that at my own company, but maybe I can't quote unquote get away with that by putting that in the Lucene sandbox?
I
or?
think as long as the final files that your codec format produces are seen through the directory API, I think it'll work fine. You can do whatever you want temporarily, but the final artifacts, I think, have to go through directory API.
Well, sure. That's always understood. Like I mean, these things in Lucene talk to the directory API. Oh, so maybe you're saying that the directory API doesn't quite necessarily give you the flexibility to do some creative thing.
Yeah, like
But
append
could-
only. And you
Okay.
can't open a file that you're still writing.
You can write to a temp directory though, and you can. Anyway,
Yeah.
you found something better. So I'm not saying you shouldn't have done what you did, but was just wanting to understand the limitation.
Yeah.
Yeah, if you get your hands dirty actually implementing that, that will, what the situation you described involves a, say, open an input from the directory. If you try to read that output, you just cannot get it through the directory. Maybe it's still not written yet, or it will just error you out if you ever get there.
Yeah.
It will be forgetting. If you use an index input and index output, then you cannot like do that. But I mean, like it's just Java, so like you can like do
Yeah.
something out.
Yeah, if
So,
you bypass
so
the
if you want a
directory-
clean directory abstraction implementation, you have that limitation. But if you know you're talking to a file system, which it is, then yeah, I get
Yeah,
it.
we
Okay.
probably could have gone underneath the directory API to do the reading as it's writing.
Yeah.
I think
It's ugly. I'm not
Yeah.
not
But
championing
cache,
this. I just
cache seems like a nice solution because it's a small amount of memory. And
I love your solution.
Yeah.
Yeah. I-
And there's a knob. If you want minimality, you want to spend the RAM, you can crank that knob up. You burn more RAM during indexing, but you get a smaller FST.
Yeah.
So you have that nice flexibility.
Also, like one thing I didn't mention earlier, but previously, like there's a minor but very annoying issue in FST, Lucene FST, is that like there's not an easy way to like control the tool FST memory
Horrible
usage.
parameters, no one
So
understood
there's a lot
those.
of-
Yeah, I completely agree. It's totally unusable to outsiders.
There's not variable that like no one understands like how it works. But now like you can have a
He's got
like
one,
simple
yeah.
node that can direct FST how much memory you can use for the suffix.
yeah.
It's much more intuitive now. There's just the knob of how much RAM.
So there were tuning parameters, no one knew how to use them. Now we have one we can use.
Is there another question?
So David, we got one question. Could you go to one of the diagrams that shows the FST? I just had a question about the layout, like how it is laid out on the disk.
The example.
What?
That one, yeah.
That one. So when you're laying out in a byte array format, is it like M, O, P? Like is it like pre-ordered, or first it would lay out M, P, S, T, or like in the disk?
It kind of grows backwards.
Yeah.
Oh,
So
it goes backwards.
Like that P arc at the very end, it would start there.
yeah.
And then an H, and then a T. It sort of it freezes backwards.
So the
And then the whole FST it goes in reverse. After it's done writing, you read it backwards. Like the start node is at the end, and it goes backwards, which is really bad for the operating system because they always think you're going to read ahead.
I was
So,
thinking like
read
whether
behind,
it
yeah.
would affect the CPU cache. Like would it do some more misses if I read? Like it's the similar problem with a binary tree. Like if you store it pre-ordered or.
Yeah.
We tried reversing it once, I think, and didn't get very far with it, but maybe.
We used to have a way to reverse it, and we removed the code because it was so hairy and complicated. It was, yeah. But we've thought about bringing back just the reversal. The thing we removed was like an optimizer that would make it smaller and do the reversing as a side effect. We've thought about bringing back just the reversal because maybe that's easier than trying to include the optimized code. But I don't think we've really succeeded in bringing it back and testing it. I suspect there's a win there.
I think that I still saw the issue open. That. But,
Yeah. And conceptually, it's kind of an easy renumbering. Like if you could just sort of do it right, it should just be straightforward.
So also interestingly is that like when we build FST, so we first like write it in the forwarding directions, but when we like free that, we somehow we write backwards. So I also try to like just skip that, just for everything forward. But yeah, I think they also like maybe something is, I think the code is a bit convoluted, and it's also we may also need to like change some other part to make it work.
Just
Yeah,
on
I
the
think-
same topic, is it possible, let's say we use a sort that sorts the input tokens reversely? Like, for example, for the input mob, you don't change the string, but let's say we implement a custom sort that will sort reversely. So basically treating mob as POM. And then, would that help? And then we add each input in reverse order, like add P first, so that we sort of freeze forward.
That's cool. Reverse it up front instead of at the end. That's a good idea.
Tweaking the tool.
It's hard to think about.
But reason lies the rate is still backward. and it still have the program.
Yeah.
That's
Because you have to pre-reverse the term you're going to look up at search time, and
No,
then you still go backwards.
You kind of rate it as the
Well, yeah,
I mean, you
it's
rate
not
it
a-
from the suffix.
It's not a bidirectional arc. Those arcs only go in one direction,
I see.
so you
okay.
can't traverse it backwards.
I see. So the
I
output
see.
comparison will be broken.
That might be okay, but the input, you can't traverse the FST backwards.
Well, also the sorting will be all messed up.
Can you
won't
store
it?
it somehow backward, the arc? Like
Really
when you
try.
store the arc, you know, like
Yeah.
We are on time, but
Let's
the
start
next-
writing it.
Yeah, but the next talk, we don't have the speakers for the next talk, and so
We have a lot of time.
Oh.
we have time if we want to continue the discussion, unless I'm going to attend another talk.
Someone break out a laptop and start coding it. We're there.
One last question, since we're going slightly over for that reason. So I was a little slightly unclear on the final state of things. So, like, what's in? If you don't mind, can you go back to the last slide that says what's been? We're just a little unclear. Like, what is not released that should be released, or you will release, but maybe, or I was just.
So like the FST, the core data structure, and it is used in many ways. So we only support the option to build it off-heap. And but there are also some other part we will see like the synonyms or
Okay.
some other part.
Sure.
We still need to explore that
Sure.
options.
But the off-heap building has been released since like 9-something, right? 9.7, 9.6,
10 something.
10. Oh, it was a 10.0 only change?
Oh no, yeah, I think 912.
9.12. Okay. Okay.
By the way, when you say off-heap FST, I mean off-heap FST been around since 7.2. You're talking about writing. You didn't say write it. Like this is off-heap writing. Right there.
Yes, off-heap
Yeah.
writing. Sorry, you're
Yes.
right. Yes, there was an off-heap reading a long time ago.
Oh yeah. Very aware of
Yeah,
that.
yeah. Lucene in general has been moving everything off heap. So now off heap writing, as of 9.12, it's available, and 10.0, 10.1, 10.2, soon 10.3. Did the RC2 vote pass? Figure? It passed? Are the bits out?
It's still open, but looks like it should pass.
Great.
I would
We're in
say
our
the
cool
minus
down
98.
period.
Famous last words. It looked like it should pass. I'm gonna go vote now.
You had 3 votes. We're just waiting for non-minus ones.
Yeah, I haven't seen the minus one.
Great. Uwe and Robert are happy. Great.
It's Chris who beat it.
How about with Jenkins?
That's right.
I got a lot of email from policemen this morning. I don't know.
Okay.
No other answer.
More questions?
Thank you.
Thank you
Thank
so
you.
much.